তোমরা প্রত্যেকে রেসপন্ড করার চেষ্টা করবে, যে প্রশ্নগুলো জিজ্ঞেস করবো ডিসকাশনের সময়, ঠিক আছে? তোমরা পার্টিসিপেট করার চেষ্টা করো, তাহলে শিখবে। তো আমি বলেছিলাম যে ডিজেনারেট পার্টারবেশন থিওরিটা আমি রিপিট বলবো, তাই তো? তো লেটস স্টার্ট the rediscussion on degenerate perturbation theory. Degenerate perturbation theory. Okay. So already we have obtained the formula for first order and second order correction for non-degenerate system. Suppose you have a system with distinct unperturbed spectrum. Unperturbed spectrum. Okay. So such systems are called the non-degenerate system, because suppose the Hamiltonian of the unperturbed system be H naught. So H naught of N naught, it is basically En naught N naught, and the eigenvalues are essentially different. That means suppose E1 naught less than E2 naught less than E3 naught, and they are not equal to each other. So that means the system possesses a distinct set of unperturbed spectra. That means the energy eigenvalues of different states are different. So that's why the system is degenerate, non-degenerate system. Okay. So for non-degenerate system, you have the correction terms for energy is, suppose En1, that means the first order correction term in the energy, which is H prime of Nn. That means N naught H prime N naught. The first order correction term in energy, and the first order correction in the state, which is denoted by this N1, which is minus of summation over k of course not equals to n, which will be like that, k naught H prime N naught of k naught by ek naught minus n naught. Okay. En1, that means the first order correction in the energy level, and this is the matrix element, diagonal matrix element of H prime. Okay, and the matrix should be written in the unperturbed basis. Okay. So these are the correction term in energy eigenvalues and the corresponding states in the first order correction. So up to first order you can write suppose En lambda, which will En naught plus lambda of H n up to first order, and N lambda, which is N naught minus lambda of summation over k naught equals to n, and this is H prime of kn, right? Kn element of the matrix of K naught by En naught minus K naught. Okay. Okay. This is our description. This is our description for the first order correction for non-degenerate case. Now take an example of degenerate case. Simple example. Simple example of a two-level degenerate system. Two-level degenerate system. This is just an example. Okay. So that means the system will possess two states, two one part of states having same energy eigenvalue. So suppose the unpart of Hamiltonian E1001. Okay, so this is the unpart of Hamiltonian, and this unpart of Hamiltonian has two states, two spectra. One is suppose 1 naught, and the matrix form of 1 naught should be 10. You know from the matrix diagonalization, the eigenvectors or eigenmatrix of any matrix can be written in that fashion. Okay, so this is basically one of the eigenstates, and another eigenstate is suppose 2 naught. It is 0 1. The second one, column by column, is written to diagonalize the matrix. So this unpart of Hamiltonian have two distinct two distinct spectrum or two distinct eigenstates having the same energy eigenvalue. The energy eigenvalue is E, and here also E. Okay. This has the eigenvalue E, and this has also the eigenvalue E. Okay. So this is the scenario for unpart of situation. Now we are going to perturb the system by the perturbing Hamiltonian. Say it is suppose epsilon 0 1 1 0. Okay, so this is our perturbing Hamiltonian. Okay, now suppose try to apply the degenerate, try to apply the non-degenerate formula. Okay, so suppose previously or primarily we may consider that the non-degenerate calculations or the non-degenerate formula may be okay with the degenerate one. Now, following this formula, what will be the first order correction for E1? Which will be H prime 1 1. So now the value of H prime 1 1 be 0 because it is off diagonal matrix. So this is 0. And E21, it is also H prime of 2 2, which is 0. So following the non-degenerate formula or non-degenerate procedure, at least up to the first order, there is no effect of the perturbation. There is no effect of this perturbation on the system because the energy eigenvalues remain same, and essentially the degeneracy is not over. The degeneracy still exists. Okay? The degeneracy was for the unperturbed system, and even after the perturbation is applied on the system, the degeneracy still remains there. Okay, so this is the outcomes when you try to apply the non-degenerate formula on a degenerate system like this. Okay, now we are going to find the effect of perturbation directly, and you know H is equal to H naught plus lambda H prime, right? So if you put the form of H naught and H prime, then it should be E lambda epsilon, lambda epsilon. If you put the form of matrix here, the original form of H naught and H prime, and then you can find the eigenvalue of this matrix. Okay, what is the eigenvalue of this matrix? H minus determinant of H minus lambda I is equal to 0. Then it should be suppose lambda. Suppose I am writing suppose alpha. Okay, so alpha is the eigenvalue. Then it should be E minus alpha lambda E. Okay, and lambda E E minus alpha. Okay, this is 0. So E minus alpha is equal to plus minus of lambda E. Okay, so alpha is equal to lambda alpha is equal to E minus plus of lambda epsilon. So there are two eigenvalues for this matrix. One is E plus lambda E and another is E minus lambda. Okay. So when you take the direct approach to find the eigenvalues, you have two eigenvalues. Okay. One is suppose E1. Okay, E1 of lambda up to first order. So this is E plus lambda epsilon, and another is E2 of lambda. Yes, E minus lambda epsilon. So now, if you find the eigenvalues of this matrix directly, then you can say that after perturbation, this is the effect of perturbation. After perturbation and in the first order, the degeneracy is broken, having different energy eigenvalues for the eigenvectors. And you can make the better calculation or further calculation to find that the corresponding eigenvector of this is 1 plus 1. Okay, and this is 1 minus 1. Okay, so after direct calculation, the result is totally different from the cases when you apply the non-degenerate procedure for this degenerate system. The direct calculation will yield you the broken degeneracy in the first order, having different energy eigenvalue and the different eigenvectors from the unperturbed. Okay. But the non-degenerate calculation cannot reach up to that effect. The non-degenerate calculation will yield that there will be no change in the first order. So you can't apply the non-degenerate procedure for a degenerator. So this is the take-home message from this exam. You can't apply the rules of non-degenerate case for degenerate. Okay. So you have to develop the different tools to find the effect of perturbation for the degenerate case. And how can you make that? How can you develop that? There is a hint here. There is a hint from this exam. Because suppose this is psi lambda. So psi lambda is 1 by root 2 of 1 1. So this is psi 1 lambda suppose, and psi 2 lambda is 1 by root 2 of 1 minus 2. And you can write this one as 1 by root 2 of 1 naught plus 2 naught. Okay, 1 node means column matrix 1 0. 2 node is column matrix 0 1. And if you can add them, we'll find in that way. And similarly, this is 1 0 minus of 2 0. So what does it mean? This means for degenerate case that degeneracy will be over due to the perturbation, as well as the new basis, the new spectrum is not the brand new. It is the linear combination of the unperturbed case. The perturbation will transform the basis from the unperturbed situation to a new situation. Okay. In non-degenerate case, the effect of perturbation is to change the state slightly. Okay, you have found already. Suppose n naught will go to n lambda, and this n lambda is will be n naught plus lambda n1. So those are the effect of non-degenerate perturbation. But in degenerate case, it will not yield the brand new. It will not yield the brand new spectrum. It will yield the linear combination, a suitable linear combination of the unperturbed basis. This is 1 0, this is 0 1, and a suitable linear combination will yield the perturbed. So this is the hint, or this is the hint from the previous example. This simple example will give you this hint. Okay, and taking this hint, we have to develop a complete theory. Okay, so now let's think it in more general way. Okay, so suppose in general you have a system. You have a system with 4 levels. Suppose I am taking any ordinary system with 4 levels. One is psi 1, psi 2, psi 3, and psi 4. Now this psi 3 and psi 4, they are non-degenerate. Okay, that means they have the different energy eigenvalues. But psi 1 and psi 2, they are the degenerate states. That means they have the same energy eigenvalue. So you can write this, suppose En naught, that means E1 naught of psi 1. Suppose for unperturbed basis, I am writing this one. Psi 1 naught is E1 naught psi 1 naught. H of psi 2 naught is equal to E2 naught on psi 2. And suppose E1 naught equal to E2 naught equals to suppose E naught. So this is a twofold degeneracy of the system. Two different states has the same energy E naught. And other two are non-degenerate. So H of psi 3 naught is equal to E3 naught psi 3 naught. H of psi 4 naught E4 naught psi 4. Okay. So these two are degenerate and these two are non-degenerate. Okay. The non-degenerate case are trivial. They are not problematic. You can apply the non-degenerate rules for these two cases. But these two are problematic for non-degenerate formulas, because suppose you are going to find the first order. That means suppose psi 1 1, first order correction to the state. Then it should be minus summation over k not equals to 1. Okay, k not equals to 1 H K1 prime of K naught by Ek naught minus Y. Okay, and here already you have found E2 naught equals to E1 naught equals to E naught. So when you put K equals to 2 here, the whole term will be undefined. So you can define this correction term for psi 1 and psi 2. Okay. The similar thing will happen for psi 2 also. Suppose for psi 2 1, it will be same. So these two states, psi 1 and psi 2, are problematic because they will yield the undefined terms in the first order terms. So how can you handle this? How can you handle this? You can handle this issue by taking suitable coordinate, suitable basis transformation. Suitable basis suitable basis transformation. Okay. So this psi 1 not psi 2 not is to be transformed in a suitable set of bases. Okay, in a suitable basis. Suppose I am writing phi 1 not and phi 2 not. Suitable basis. So the degrees of freedom was twofold degeneracy. So after transformation, it will yield again the twofold system. So this phi 1 not and phi 2 not. So this is the subset of the original system because you already have other two states, psi 3 and psi 4, but we are concentrating on the degenerate levels. So you can transform the degenerate states into a suitable basis so that this matrix element of H prime, suppose H prime 2 1, that means in the new basis, in terms of the new basis, it should be phi 2 not H prime phi 1 not is 0. So you can make a suitable basis transformation in order to make this corresponding matrix element to be 0. So hence, in this case, suppose you put 2 equal k equals to 2, then it will be 0 by 0 case. And in this limit, 0 by 0 will be finite. So the term will not be undefined. You can resolve these undefined terms by making suitable coordinates, suitable basis transformation so that the corresponding matrix element will be 0. Okay. So this is the key approximation or the key ideas regarding this degenerate perturbation theory. The key principle is here, you have to make suitable basis transformation to find the corresponding matrix element of the perturbing Hamiltonian to be 0. And in that way, you can avoid this divergence. That means the undefined terms in the correction. In the correction terms, first order correction. Okay, so this is the idea. Okay, how can you proceed in the degenerate case? This is the challenge for you. How can you proceed in the degenerate case? Okay, so you have to make the suitable coordinate transformation. Sorry, it is not the coordinate transformation. It will be the basis transformation. So arbitrarily, I am taking suppose C. উপরে C লেখা আছে. Okay. So phi 1 naught is basically suppose S11 of psi 1 naught and S21 S21 of psi 2 naught. Okay. And phi 2 naught is equal to suppose S12 of psi 1 naught and S22 of phi 2. So once you find this suitable basis transformation, then you can resolve the degeneracy. Okay, so your job is to find this coefficient of transformation. Basically, this is a matrix. You can write this one in a linear transformation of way. Suppose phi 1 naught, phi 2 naught is equal to uh, psi 1 naught, psi 2 naught. Okay. Then it should be S11, S21, S12, S2. So in that way, you have to find this matrix. This is suppose S matrix, the transformation matrix, or it is called the Jacobian. So you have to find the suitable Jacobian so that the corresponding matrix element, this condition must be satisfied, essentially satisfied. Okay, so this is your job in hand. How can you find this transformation coefficient? Okay, and it is also noteworthy that this phi 1 node and phi 1 node and phi 2 node, these are also the eigenvectors of H naught having the same energy eigenvalue E naught. Okay, you can check this one. H naught of phi 1 naught, it will yield E naught of phi 1 naught. H naught of phi 2 naught, it is also the same E naught of phi 2 naught. So these two have the same uh, energy eigenvalue E naught. Okay. So now this is the procedure to resolve the degeneracy issue in the perturbation method. So it will be clear if you discuss some example in this regard. The example is dark effect to Hamiltonian to hydrogen atom. Okay. So you know the unperturbed hydrogen atom with Hamiltonian H naught. H naught is basically this is a two particle system, two body system. One is nucleus and another is electron. But you can effectively write it as it is a one body system in the relative coordinate system, which is 1 by 2 mu minus h cut square by twice mu of grad square plus minus of e square by 4 pi epsilon naught r. And you know the solution of this Hamiltonian, minus 13.6 electron volt by n square. Okay, so En naught is equal to minus 13.6 electron volt. That part of spectrum of hydrogen. Okay. Now we are going to perturb this system. Then you have to provide some interaction, provide some disturbances from the outside. So here we are going to supply this perturbation in terms of the electric field, and this is static electric field. Static. So due to the effect of electric field, the atom will get polarized. Will get polarized, and whenever a dipole will be aligned in the direction of electric field, it will gather some potential energy, and this potential energy is the perturbing Hamiltonian minus P dot. And so this will yield some constant having electric field along z direction. So This is suppose some alpha of cos theta. Some constant multiplied by cos theta. Alpha is a constant. You can say. Okay. So this is H prime. Okay. And in the reality, you have ground state, which is E1, and the fast excited state, this is E2. So in the second energy level, you have 4 degenerates. This means this is n equal to 2. For n equal to 2, L may be 1, L may be 0. Okay. For L equals to 1, there will be 3m, 1, 0, minus 1, and here m have only one value, which is 0. So basically there are 4 degeneracy in the fast excited state of a hydrogen atom. 4 degeneracy. Okay. So this is n equal to 2, this is also n equal to 2, and you have L equals to, equals to 0, this is L equals to 1. For L equals to 1, there are 3 states having same energy again. And also here, this is just the same energy again, L equal to 0. Okay. So the 4 states can be denoted by quantum number notation, which is 2, 0, 0. Another is 2, 1, 0, 2, 1, 1, and 2, 1, minus 1. 4 levels. This 2 for n. So n is same for all. So the energy levels depend on the n only, because n is the energy quantum number. Okay. So these 4 states have the same energy eigenvalue, which E2 naught. So suppose this is writing I am psi 1 naught. This is psi 2 naught. This is psi 3 naught, and this is psi 4 naught. Okay. Now you can say that these 4 have the same energy eigenvalue. So this means all are the degenerate. All the 4 states are degenerate. But these 2 are not the troublesome terms, because if you want to find the matrix element of H prime corresponding this 3 and 4, you can check that one. It is very easy to verify. Suppose this is H prime 3 1 equal to H prime 4 1 equals to H prime 3 2 equals to H prime 4 2 equals to H prime 3 4 equals to 0. Okay, H prime 3 4 is equal to 0. Because this 3 state and 4 state, they will not connect the other terms with the Hamiltonian H prime. They will yield the 0 matrix element of H prime. Okay. Yes. This means the corresponding matrix element of H prime associated with 3 and 4 will always be 0. Okay, 3 1 4 1. Any row or column, if be associated with 3 and 4, it will give 0. So this Hamiltonian, Hamiltonian, or the matrix of the Hamiltonian, is not troubled with this 2 1 1 and 2 minus 1, 2 1 minus 1. Okay. So you can treat them in the non-degenerate case. Okay. You can treat them this 2 1 1 and 2 1 minus 1 in the non-degenerate. But the troublesome terms are that 2 0 0 and 2 1 0. 2 0 0 and 2 1 0. They will not yield non-zero. They will not yield the zero matrix element. Okay, so this is not zero. 200 H prime 210 equals to, these are Hermitian, so 210 H prime of 200, this is not equal to 0. Suppose I am writing this is say suppose beta E. Of course, this matrix element will be linearly proportional to the electric field. Thus, I am writing this is suppose beta E. E is the static electric field. Say. So then we have to make the transformation from psi 1 naught and psi 2 naught. That means 210 and 200 to phi 1 naught and phi 2 naught. So you have phi 1 naught, phi 2 naught is equal to S11, S21, S12, S22 of 200, 210. That means psi 10 and psi 2. So this is the transformation you can make. Okay, this is the transformation you can make. Now you can apply this one for the correction terms you have made in the non-degenerate case for lambda to the power 1. Can you remember the equation for lambda to the power 1 of the coefficient of lambda to the power 1? Okay, can you remember? Else we have to go to the Jamboard page. This one. Okay. This one. H naught of E1 naught. Okay, the equation is H naught. Then okay. So you have to collect this one H naught minus N naught. The term is H naught minus N naught of N1, right, equals to equals to En1 minus H prime, En1 minus of H prime of N0. So this is the governing equation to find the first order correction. Now you can apply this one for phi 1 and phi 2 also. So this is H naught minus En naught U1 naught of phi 1 1, first order correction to the phi. Okay. Then it is E11 minus of H prime of phi 1 naught. Okay. And what is phi 1 naught? Phi 1 naught, and write H naught minus E1 naught of phi 1 1 equals to E11 minus H prime, okay, of phi 1 naught. Phi 1 naught means S11 of 200 plus S21 of 210. Okay, this one. Now at first, hit the brow of 200 at the both end. Okay, the brow of 200 at the. So if you hit this one at the left hand side, it will yield 0, because H naught over 200 it will yield E1 naught. So E1 naught and minus E1 naught will be 0. Or at the right hand side, you can write 200 E11 minus of H prime. Then this one S11 of 200 plus S21 of 210 equals to 0. Okay. Then first term E1 is just a constant. So 200 and 200 are orthonormal state. So it will be only E11 into S11. Okay. Then these are orthonormal. So second term with each 210 will be 0. Then 200 200. Okay. Minus of 200 H prime of 200, which is basically 0. This is off diagonal matrix, so this is 0. And then you have minus 200 H prime of 210 of S21 equals to 0. Okay. So E11 of S1 minus this matrix element of S21 is equal to 0. Then you can write S11 of E11 equals to, this is beta E, so beta E of S21. S2. Okay. Similarly, you can hit the brow of 210 at the left hand and right hand side. And in the similar fashion, the left hand side will be 0. And in the right hand side, you have S21 of E11. This is S21 of, this will be suppose E11. Okay. Then S11 of beta E S1. You can check the calculation, very easy. And you can hit the brow 210 at the left hand and right hand side. And the similar kind of calculation, you can find this one. Okay. So now you can write this one as S21, sorry, S11, S21 with 0 beta E and beta E of 0 is equal to S11, S2 of E11. Okay, you can check this one because this is beta E S21 equal to E1 S11. This equation, these two equations can be written in the matrix way. Okay. So this is an eigenvalue equation. This is an eigenvalue equation. You can write minus of E11 beta beta of E beta of E minus of E11 multiplied by S11 S21 equals to 0. Okay, you can take this on the left hand side and after the matrix operation you can find this one. So this is the eigenvalue equation of this matrix and you can find two values of E11. That means the similar kind of calculation will be found for the second one, that means for 520. Okay, I have made the calculation for 510 only. This is for 510. Similar kind of calculation will be found in the 520 case. And you have found the similar kind of eigenvalue equation for that. So this is a basically pair of equation. Okay. And from here, this correction term have two different values. Okay. This correction term has two different values. One can be recognized as E11. Okay, one can be recognized as 211, and you can get from here E11 have two values, plus beta E and minus beta, two eigenvalues, and one can be taken as E11, which is suppose beta E, and another is E21, suppose this is minus beta E. Okay, so now the degeneracy will be broken. Now the degeneracy will be broken. Okay, so there are four levels, which is one is 0 0, 1 0, 1 1, 1 minus 1. 2 is for same for all. And after the perturbation, this 1 1 and 1 minus 1 remains same. 1 1 and 1 minus 1 remains same, having energy E naught. Okay. But these two states transform to a superposed state of 0 0 and 1 0. One is 510, and this 510 is nothing but the superposition of 210 and 200. That you can find the value of S11 and S21, and you can find this 1 and 1, and another is goes 520. This 520 will be 1 by root 2 of 200 minus of 210. and they have the different energy eigenvalue also. This will be E naught plus uh, beta E, this is E naught minus. So these two have the broken degeneracy after the perturbation is applied, but these two states are still degenerate, and you can find the broken degeneracy in the higher order perturbation, maybe in the second order perturbation, but we can't guarantee that you can find it in the second order. You may go to the further higher order perturbation also, but till this first order correction, these two, the degeneracy of these two states is over, and you have the distinct energy. Okay, and the correction is linearly proportional to the electric field. So that's why this Stark effect is called the linear Stark effect. This is linear Stark effect. And similar kind of correction term you can find in the second order for these two, which will be proportional to E square. So I am giving the homework for you to find the second order correction for 1 and 1 minus 1 state, and which will be essentially proportional to E square. That's why those correction will be called the quadratic Stark effect. These are the linear Stark effect because the correction term is proportional to the electric field, and for the higher order perturbation for 1 and 1 minus 1 will be quadratically proportional to E. So that's why the quadratic Stark. So this is the example and procedure of degenerate perturbation theory. Okay. So this linear Stark effect is the perfect example of degenerate perturbation theory. How you can make the correction. Okay.